Extracting hydrocarbons from the seabed is a constant battle against physics. This simulation shows pressurized gas forcing its way through microscopic rock fractures. Deep beneath the ocean floor, geological forces exert immense outward pressure. In these high-pressure, high-temperature zones, reservoir fluids can reach 15,000 psi. On a drilling rig, hundreds of personnel live and work in the immediate vicinity of these forces. As shown here, accommodation blocks are positioned mere inches away from highly pressurized process modules and drill derricks. No single component can withstand these variables alone. Maintaining safety in this environment requires a meticulously nested defense-in-depth architecture. The 2010 Macondo well blowout was a failure of that architecture. The Deepwater Horizon disaster was the result of a systematic sequential breach of every layer designed to keep the well under control. To understand offshore engineering, we must deconstruct the specific mechanics of containment by studying exactly how they catastrophically fail. The Macondo well reached extreme depths. This cross-section shows the rig in 5,000 feet of water, with the wellbore descending 18,350 feet into the seabed. At the bottom, where the wellbore meets the reservoir, the first line of defense holds back the crushing formation pressure. During active drilling, engineers rely on drilling mud. This dense, specially formulated fluid is pumped down the well to create a hydrostatic overbalance that physically pushes back against the reservoir fluids. While the drill bit is turning, this carefully calibrated column of fluid pressure is the only thing preventing a blowout. Hydrostatic pressure provides temporary containment, but completing a well safely requires the installation of a permanent physical seal. That physical seal is established through cementing. This is the primary barrier designed to lock hydrocarbons beneath the surface for the life of the well. The process involves pumping cement slurry down the casing and using wiper plugs to force it up the outer annulus. This fills the void between the steel pipe and the rock, creating a tight seal. Engineers verify this seal using a cement bond log. By measuring acoustic waves, the log can distinguish between the solid bond, seen here on the left, and the flawed, gap-filled section on the right. At Macondo, the primary barrier was compromised from the start. The specific cement mix was flawed, failing to cure properly and allowing gas to form channels through the supposedly solid seal. The rig crew missed the failure because they misinterpreted a negative pressure test. They assumed the well was sealed when the data showed the primary barrier was already leaking. With the cement compromised and the operators unaware, high-pressure methane gas began a silent race up the wellbore towards the surface. If the primary barrier fails, the secondary defense is the blowout preventer, or BOP. This towering stack of valves sits on the seabed and contains multiple nested layers of mechanical rams. The most critical components are the blind shear rams. These opposing metal blades are designed to physically cut through the drill pipe and seal the wellbore entirely in an emergency. During the blowout, the BOP was triggered, but the blind shear rams failed to fully close. They could not sever the drill pipe because it had been pushed off-center by the force of the escaping fluids. Mechanical defects and the extreme dynamic flow of the gas prevented the blades from meeting, meaning the ultimate mechanical barrier was defeated. With no remaining barriers at the seabed, the high-pressure gas surged directly into the drilling rig's topside systems. When the gas reached the Deepwater Horizon, it entered the process modules. At this point, only human intervention could prevent a fire. Operators made a fatal error by routing the volatile well fluids into the rig's mud-gas separator instead of venting them directly overboard. As this simulation shows, the high-pressure gas expanded so rapidly that it overwhelmed the separator's capacity almost instantly, leading to a violent vessel breach. This rupture released a cloud of explosive gas directly onto the rig floor, where it reached the engines and found an ignition source. In high-stress moments, human intervention can become the point of failure. Modern safety logic aims to remove this variable by automating every isolation step before an operator can react. We call this system the emergency shutdown, or ESD. This schematic shows emergency shutdown valves partitioning the facility into safe zones. ESD Level 1 isolates a single unit, snapping its inlet and outlet valves shut, while the rest of the platform functions. If fire or gas sensors detect a widespread hazard, the system initiates ESD Level 2, a major surface process shutdown. Level 2 triggers the riser boarding valves. These valves close to physically decouple the platform from the subsea hydrocarbons. To prevent vessel ruptures, the system then executes the 15-minute blowdown rule. The isolated topside inventory is automatically vented to the flare stack to rapidly bleed off pressure. The final tier is ESD Level 3. This sequence initiates total abandonment by shutting down main power and closing the subsurface safety valves deep inside the wells. A properly functioning ESD hierarchy acts as an autonomous immune system, sequentially isolating, depressurizing, and starving the hazard of its fuel. The cascade failure at Macondo resulted in 11 lives lost and the largest marine oil spill in history. The Presidential Commission blamed the disaster on systemic failures in risk management. No single mechanical part was solely responsible. The entire approach to safety had failed. In response, the industry adopted mandatory safety and environmental management systems. These regulations require operators to prove their staff are well drilled on emergency procedures. New consortiums like the Marine Well Containment Company were established to ensure that specialized capping stacks and response equipment are always ready for deployment. The industry has moved beyond viewing safety as a ledger of mechanical components. Safety is now managed as a system where verified procedures are as critical as the hardware. This is the ideal state of deepwater production: controlled fluid flow, active monitoring, and a fully functional chain of safety barriers. Building this state requires strict adherence to design codes like ASME B31.3, which establishes the mathematical margins for pipe wall thickness and material stress. Engineers must also perform safety integrity level assessments. These verify the entire logic loop, proving a sensor detection always triggers the correct valve closure. However, technical skill is only effective if engineers have the professional courage to resist commercial pressure and halt unsafe operations. Ultimately, the steel and cement barriers are only as reliable as the professional commitment to maintaining them. Containment survives when the engineer prioritizes systemic integrity over everything else.